Yes, we can begin. Maybe can you share the screen?
Yeah.
Yes. So today's third speaker is Rodrigo Quaglia, and he's going to talk about post-inflationary enhancement of adiabatic perturbations.
Yes. So welcome everybody. First of all, thank you, Anish, for the nice invitation and for organizing this nice seminar series. As you mentioned, my name is Rodrigo. I am a fourth and last month's PhD candidate at the University of Groningen in the Netherlands in a dual program with the University of Mexico in Mexico. And today I will tell you about our most recent work in this business of multi-field inflation, where you can source the scalar perturbations from one another. This was, should I stop?
No, no. But can you try
Just
to make can you try to make it full screen?
It's already full screen. This is, I don't know why, but this is the
Ah,
fullest screen that I can do it.
I see. I see. No, then it's fine. Please go on.
Okay. As I was mentioning, this work was in collaboration with some people here in Groningen, namely another fellow PhD student, Martino Michelotti, one of my supervisors, Diderik Rust, and the group of Stanford led by Andre Linda and Renata Kalosh, and John Joseph Carrasco from Northwestern University. And so let us start. This is the outline of my talk. I will start with a review, very quick review of what is single field inflation in order to just set the stage for everybody to be able to understand what follows. Then I will move on to the multi-field case. And I will especially focus on the sourcing of perturbations that I was telling you about in the first slide. Then I will move on to a specific model which we studied in this paper, which features the post-inflationary sourcing of perturbations, which is the main the core of this talk. And I will lastly just finish with some summary and conclusions and some final remarks. So, inflation is this thought epoch of accelerated expansion in the very early universe. Originally, it was motivated to some of the lambda CDM initial condition problems. So, for example, the flatness and horizon problems. And in its vanilla version, it is just a minimally coupled scalar field, phi in this case, coupled to Einstein gravity. In this scenario, we have two equations of motion. One is the Friedman one, which tells us the fate of the universe, basically h being the Hubble factor, being the ratio between the derivative of the scale factor and the scale factor itself, will tell us how the universe evolves according to some matter content, which in the case of the single field inflation model is just dictated by the scalar field known as the inflaton. And the second equation of motion is the Klein-Gordon equation of motion, the dynamics of the scalar field. And those, there are many ways in which we can achieve an inflationary potential. In this talk, I will only focus on these type of potentials that I'm showing you here, who have the characteristic of having a very flat region. Why is this? Because if we look at this dynamical system, if we propose a model or a potential with these characteristics, namely it being very flat, we immediately notice that the flatness of the potential implies that the value of the field is quasi-constant, and thus we can throw away the first derivative or its kinetic energy in the first equation, and thus we achieve that the Hubble parameter goes as the potential, but we recall that the potential is almost flat, almost constant, and thus it immediately gives us exponential expansion. This is the quickly way to see why a flat potential is needed. And so what is remaining to do is to quantify this flatness, to say when a potential is sufficiently enough flat to be able to carry on inflation. And this is done by the introduction of these slow roll parameters, epsilon and eta, which are simply basically ratios of the derivative of the potential and its derivatives. And we thus say that inflation can occur whenever these parameters are slow, which then means that the potential is sufficiently flat. And this is basically in 2 minutes the background story of the inflationary model of single field inflation. However, After these models were created or developed, people realized that the true signatures, observational signatures, and heavy consequences of inflation didn't come from the background, but from its perturbation dynamics, which in the case for the vanilla model of inflation are of two types, namely the scalars, which are the seeds for the CMB anisotropies we measure in the sky, and also the large scale structure in our universe, and also the tensors, which are these primordial gravitational waves which we haven't still measured today. Here I am presenting you both these perturbations. For the scalars, we have what is known as the curvature perturbation, which is a combination of background and perturbation quantities of the inflaton. And on the tensor side, we have the transverse traceless metric degree of freedom. And what is important of these two equations of motion is that they have two limits, namely when the modes are inside the horizon and when the modes are outside of the horizon. We can understand this in the following way. In subhorizon limit, we simply reduce the equations of motion to these ones, and we immediately notice that the general solution for both the scalars and the tensors is an oscillating mode, like a plane wave. And on the opposite regime, when the modes are outside of the horizon, they are simply a constant amplitude because the decaying mode will saturate. So this is telling us that if we imagine the horizon of the universe being, for example, like a sphere, and then a mode oscillating with some given wavelength, then we can imagine that if the horizon is bigger than the wavelength, let's say the horizon is big like this and the wavelength is oscillating inside the horizon, then somebody inside the horizon will actually see the oscillations, and then we'll be able to see what happens in this regime in the left-hand side of the plot, namely that the perturbations will oscillate. However, in the opposite regime, when the horizon is, say, like this, and the perturbation has a very large oscillation, then from somebody inside the horizon, it looks like the perturbation is frozen. So that is why, at the qualitative level, we can understand why the perturbations inside the horizon oscillate, while outside the horizon, they freeze out. And this is exactly the reason why we can prove inflationary physics, because this is exactly what happens during inflation. During inflation, perturbations are generated inside the horizon, they oscillate, then there is a moment of horizon exit or horizon crossing, and this perturbation's amplitude is frozen out, until they re-enter the horizon in later epochs in the history of the universe. So this allows us to prove things we are seeing today with physics at the end of inflation. If, on the contrary, on superhorizon scales, for example, the curvature perturbation would not freeze out, then we would need to know the entire evolution of the universe following this perturbation in order to be able to track its evolution up until the moment we measure it, say, for example, today. So again, this is in short the key elements of single field inflation. So now let us move to multi-field inflation. This is basically the generalization of the action I showed you earlier, in which we allowed for several scalar fields to be present or be dynamically relevant during the period of inflation. These scalar fields are coupled both by the multi-field potential B and also via this internal metric or field space metric, GIJ. In general, we can find the two equations of motion again, the Friedmann equation of motion, which is very reminiscent of the single field case, and the Klein-Gordon equation of motion. And as in the single field case, we can again define the slow roll parameters in order to know when inflation can happen. And this is just to say that in multi-field inflation, it is not that one field is responsible for inflation and then the others are spectators or do not contribute to the dynamics. It's the whole multi-field dynamics which drives the inflationary period. This is very important to keep in mind, because as I was saying, it's not that one field is particularly responsible for inflation, but the whole system is responsible to give this accelerated expansion. And most importantly, let us now discuss the main difference between single and multi-field inflation at the qualitative level. In single field inflation, as I told you, we have one field, then our field space is one dimensional, and then therefore the background trajectory in field space will always lie in the same direction of the field. And if we consider perturbations on top of this field, these perturbations will again be aligned with the background trajectory, and therefore the moment at which inflation ends uh, is shifted just in this direction of the background trajectory. So it is as if I had the background trajectory, I have a region or a plane where inflation ends, and I simply move this plane back and forth. So this is what happens in single field inflation. However, in multi-field inflation, this is not the case because as the field space is generically higher dimensional, here I am just showcasing the two-field scenario. The background trajectory is in general a combination of these two fields, and you can immediately notice that the background trajectory is no longer aligned with the perturbations of either of those fields. So in general, the background trajectory will be in the direction of a combination of the two fields or the n fields. So it is not immediate to set this boundary of the end of inflation because the background and the perturbations are not aligned with each other. And this immediately tells us that maybe the description that I'm using here is not the best basis in order to describe these perturbations. And indeed, what we do in multi-field inflation, or what one generally do in multi-field inflation, is to transform the basis of the perturbations into what is known as the adiabatic entropic decomposition, which simply tells us that in the two-field scenario, again, from here on, I will only talk about the two-field scenario. We will have two directions. Instead of having the what would be the phi 1 and phi 2 direction, we will then shift these directions in order for one of these vectors to point always in the direction of the background and the second vector to always be orthogonal to it. So in this picture here, you can see in black a mock background trajectory that is in general a function of the two fields. And in red, you can see what is known as the adiabatic direction, which always points in the direction of the background. And in yellow, you can see the other direction, the entropic direction, which always points 90 degrees away from the adiabatic direction. So we will always have this new basis of vectors in which we will describe the dynamics of perturbation in order to clearly have one direction that follows the background and the other that is perpendicular to it. And in doing so, we can then go back to our multifield Lagrangian, expand into perturbations at second order, apply the adiabatic entropic decomposition, and then we realize that the curvature perturbation, the relevant observational quantity that I told you in the beginning, the one that sits, for example, the C and B temperature anisotropies, is proportional to the adiabatic direction, while the entropic direction is now responsible for another type of perturbation, namely the isocurvature perturbation. And then we can, once again, calculate the equations of motion for these two perturbations. In this case, we have two perturbations because we are in the two-field model. And we notice that the left-hand side of this first equation is simply the single field result, where we find the curvature perturbation. However, now it has a source term that is proportional to the isocurvature perturbation S, and this eta perpendicular, which is known as the turn rate. This turn rate is simply telling you how much does the background turn. So in the plot I showed you earlier, the turn rate is very big because it's circling around a given point. So eta is a background trajectory, and S is the isocurvature perturbation that also follows his own equation of motion. In this case, S is massive, in contrast to the case of R, which is massless. And the isocurvature perturbation S is again sourced by the curvature and the turn rate. So in a sense, we now have a coupled system of equations for the perturbations, for the scalar perturbations that we need to solve. However, if we look only at the super horizon limit, namely when the perturbations are in single field, namely when the perturbations would be frozen in single field, we found that the curvature perturbation is generically not frozen in super horizon scales, and that the isocurvature perturbation follows its own equation of motion independent of what R is doing, and its behavior will only be dictated by this effective mass. And so here we find exactly the case I was telling you in the beginning. Here, on superhorizon scales, the curvature perturbation does not freeze out generically. It depends on what S, or the isocurvature perturbation, is doing. And so, in principle, what we need to do is to have an explicit model in which we calculate the behavior of the isocurvature perturbation on superhorizon scales, namely this equation here, the second one, and then plug this result back into the equation for the curvature perturbation and find out what is the fate of the curvature perturbation, which is the relevant observational quantity on superhorizon scales. And what one will typically expect is the following. Generically, as we are talking if we are dealing with a multi-field system, we expect that already the background trajectory during inflation turns. This is to say that the background trajectory already is a function of both fields, phi 1 and phi 2, like I am plotting here. This is a mock plot just to showcase the idea. So, as the background is already turning, then we expect that the curvature perturbation is already sourced during inflation. And here I am plotting the power spectra following a single K mode, where you see that on sub-horizon scales, the power spectra does its business, and then at horizon crossing, namely when the curvature goes super horizon, we have this behavior, which is not the flat behavior one would expect in single field inflation. Namely, after horizon crossing, the curvature perturbation does not freeze out immediately. It has this sourcing due to the turning in field space, and what people usually try to do in the literature is to try to tune this turning or the parameters of the model or the model itself in order for the curvature perturbation to have an amplitude which is exactly the same one as it would have in single field inflation. So even if already during inflation there is some sourcing between the isocurvature and the curvature perturbation, usually people try or manage to find the same amplitude of the perturbation at the end of inflation that it would have if it was only single field. So this is simply showcase here if when this solid black line coincides with this dashed line at the end of inflation. So this is what one would typically expect in this scenario, as I said, because we are in a multi-field system. We expect that the background already is multi-field dependent, and if it's multi-field dependent, then it has turns, and turns mean sourcing of perturbations. So this is the what we would want to expect generically. However, we will see in a moment that we don't we cooked a model in which this is not the generic case, and we can have sourcing of perturbations even after the end of inflation. Before moving on in this part, I want to very briefly introduce what is known as the alpha tractor models of inflation. This is a model whose motivation comes from supergravity. And what it's important to know is that it is characterized by this non-canonical kinetic term for the scalar field that, once made canonical via this transformation here, develops a potential of this form, namely the hyperbolic tangent, which contains two limits. Namely, for the large field limit, we find that the potential has this particular expansion, and in this regime, this potential or this model develops what is known as the universal large field observables, which are the amplitude of the amplitude of the scalar perturbations, the spectral index, and the tensor to scalar ratio, all C and B observables. In terms of the number of EFOLs, N, and in the opposite regime, when the field is very light, or the field is very small, sorry, we recover the massive case. So what is important about this alpha attractor model is that whatever potential one includes in a model of inflation, if that potential has this same expansion where these four and this coefficient here in front of the field are generic, or they are the same ones as these two up to a field redefinition, whenever I have a potential that recreates this expansion here, I am sure that the observables that will that the observables predicted by the model will have this form here. So in a sense, the alpha tractor model is not a particular model, but a family of models. For example, the very famous Starobinsky model is an alpha attractor model for a particular value of alpha. And why alpha attractors? Well, basically here I am showing you the Planck 2018 constraints on the tensor to scalar ratio and the spectral index. Although there are some new measurements, the Planck ones really make it clear why alpha attractors is one of the most studied models or family of models, mainly because if you see the alpha attractors corresponds to the yellow curve or the yellow area that goes from the massive model up high here, which coincides with this, I don't see the color, like brown yellowish here on top, and it goes down all the way to the core or the center of the confidence regions for both the spectral index and the tensor to scalar ratio. So this is why the alpha tractor models is and has been a very widely studied model because it gave rise to the most one of the most favorable observables at the level of the CMB. And as I mentioned earlier, most recent observables have shifted these confidence regions a little bit, but nonetheless, the alpha tractor models remain a well-motivated and a very phenomenologically viable model. And so, as I was saying, we will be now constructing a model, a multi-field model that can realize this post-inflationary perturbation, sourcing of perturbations. Before moving on to this, some considerations when model building an inflationary model. As we saw from the previous plot, the polynomial potentials are in tension with observations, and at the same time, the flatness of the potential can be easily ruined by higher order corrections. And so we need to find a way to introduce different potentials than the polynomial ones, and at the same time to protect the flatness of the potential. And one possible solution is to consider a further symmetry into the Lagrangian, namely because considering a symmetry already reduces the number of possible operators that one can write down, while also suppressing them via the introduction of a large mass scale. Here I am just showing you the example of the shift symmetry. If I impose shift symmetry, then it means that I can only write down derivative couplings. And for example, the second order or the higher order derivative coupling in a Lagrangian that has this form, just by dimensional analysis will be suppressed by this large mass scale. So the introduction of these symmetries in the model building of inflation already suppresses the effect of these higher order terms. And one of the most widely spread models that uses this idea is the so-called natural inflation model, which starts with a shift symmetric kinetic term, and it breaks it down to a discrete shift symmetry at the level of the potential. And we will follow exactly this same recipe, but instead of the shift symmetry, we will use the modular symmetry. Why modular symmetry and why multi-field inflation? If we think of UV complete theories of gravity, for example, let's say string theory, these theories are usually built in higher dimensions. And when the compactification process from the higher dimensions to the form we live in is applied, usually many scalar fields are produced which encode the information about these extra dimensions. And if one of or more stay relevant, stay light enough at the time of inflation, they might be dynamically relevant. And also, this compactification process give rise to many topologically equivalent quantities, which are related by the modular symmetry. And so we can build a model in which we consider a complex scalar field, in this case tau, and we can immediately show that it is invariant under the continuous modular symmetry with this transformation here. But however, if we want to then introduce a potential in order to have an inflationary model, we cannot do it without care, because if we introduce a random potential, it will destroy the modular symmetry and it will be forever lost. However, if we want to stick with a particular set of this whole symmetry, we then demand that the potential is invariant under the discrete modular symmetry. And thus we have the model that I'm showing you here. In hyperbolic coordinates, we can thus write it as an explicit two-field model for phi and theta. And the internal geometry of the model is hyperbolic, namely because phi is canonically normalized and theta has this prefactor dependent on phi. And as I was mentioning earlier, the modular potential is invariant under discrete modular transformations. Here I am not including the specific form of the potential because it is very opaque, but in turn I am showing you the plot of the potential, which for large phi contains a very flat region where inflation will take place. And already from this plot, you can imagine that for very large values of phi, the direction theta is not apparent exactly due to the flatness of this direction. So when you go up in the potential starts to be more and more flat, and so the theta direction is not felt by the motion of the inflaton. This can also be understood by taking the large phi expansion of the potential and noticing that the first contribution of theta is double exponentially suppressed. So in a sense, it is like if we had an effective single field description of this potential. And moreover, you can notice that the expansion for large phi is of the alpha tractor kind, namely 1 minus exponential of the field. Therefore, all of this makes us believe that this model contains a single field limit in which the theta direction is not apparent. And if we have the alpha tractor expansion, our potential should reproduce the alpha tractor observables. So in a sense, at this point, this can be thought as an embedding of the alpha tractor model into a two-field model, which is modular invariant. Let me now show you the numerical evolution of both the background and the perturbations in order to verify or disprove this assertion. First, the background during inflation is given in this plot on the right. Here, during inflation, we plotted the solid lines, and the dashed lines are all the evolution after the end of inflation. So during inflation, we see that our assumption that this model is single field-like is correct because we have geodesic motion, namely we don't see the direction of theta. This field space is only moving along phi. Theta is not doing anything, it's frozen in place. However, we notice that after the end of inflation, the background very heavily turns because it is the moment when the fields start to look for their minimum. So during inflation, we have a double exponential suppressed turn rate. So the background does not turn at all. But after the end of inflation, we find this heavy turn. So already from this background plot, we can imagine that as during inflation, there is no turning in field space, we expect not to have any sourcing of perturbations. However, after the end of inflation, there is a heavy turn. So this is already pointing into the direction that the sourcing of perturbations will always happen after the end of inflation and not during inflation. Here I am showing you the power spectra following a single K mode, the CMB mode, for both the curvature, the blue curve, and the isocurvature, the yellow curve perturbations. And so you immediately notice that the curvature perturbation, the blue curve, is single field-like. It goes down until horizon crossing, and then it stays frozen. So the curvature perturbation does not feel at all any sourcing from the isocurvature one. And in turn, the yellow curve, the isocurvature one, is only again dictated by its effective mass squared, which in this case is positive. So this means that the power spectra on super horizon scales will be suppressed, as we clearly see here. So at this point, again, we confirm that this model, if we close our eyes to the evolution after the end of inflation, it reproduces exactly a single field limit. And because it contains the alpha tractor expansion, we simply would say that, again, this model is an embedding of the alpha tractor models into a multi-field setup, which is modular invariant. However, as I was telling you earlier, if we open our eyes to the post-inflationary dynamics, we immediately notice that there is an active and a very efficient sourcing of perturbations, not during inflation, but after the end of inflation. Here I am again showing you the same plot as one slide ago. In blue, you have the curvature power spectra following the CMB mode. This plot here, the left one is during inflation, and the right one is after the end of inflation, where this last e-fold here from 1 to 0 is exactly the same as the last e-fold in the left plot. So the dashed line is the end of inflation, and we immediately notice that after the end of inflation, as the background is heavily turning, we have this sudden enhancement of the curvature perturbation due to the isocurvature one. So then this allows us to think of the power spectra as two different contributions. One, which we can think of as vacuum, when the background is not turning, which happens during inflation, which is this plot here, and one sourced power spectra when the background is heavily turning, which always happen after the end of inflation, which is denoted here. In these results, we only plotted or we only numerically evolved the system 3 folds after the end of inflation, because at this point it's enough to see that the enhancement achieves a saturated point. And in doing this, we only evolved numerically the equations of motion of the perturbations that I showed you at the beginning. This is just the evolution of the curvature and isocurvature perturbations equations of motion. This is, we are not considering anything else. We are not tuning anything. This is simply the dynamics of the perturbations in the multi-field setup, given the backgrounds of our model. And so we now ask the natural question, okay, if my power spectra is not frozen after at the end of inflation or at horizon crossing, if I have a post-inflationary enhancement, how is this enhancement affecting our observables? First of all, we define the enhancement as the ratio of the sourced power spectra with respect to the free power spectra, such that the amplitude at the end of inflation is enhanced by this factor curly epsilon, and we have a post-inflationary amplitude of the power spectra. And here I am stressing that we are not changing the Kobe normalization, but simply requiring that the Kobe normalization is fixed at the amplitude after the enhancement. So the one that should follow Kobe normalization is A post instead of A end. This is usually a question people have, and here again I am stressing that Kobe is still Kobe, and we are simply shifting the moment when we need to fix Kobe to after the enhancement. So this, for example, will induce a shift in the parameters of the model, namely, for example, in the scale of the potential V0. Okay, then the remaining two observables, namely the spectral index and the tensor to scalar ratio, can be found as follows. We can repeat the same plot of the power spectra, but for different K modes, let's say different moments of horizon crossing, and then we can plot what is the amplitude of the power spectra after the enhancement, depending on the moment of horizon crossing, and we find that it follows very well a quadratic behavior. And if this is quadratic, then it means that the spectral index after the enhancement still follows the 1 minus 2 over n recipe, which is exactly the same as the alpha tractors. So in the spectral index regime, or in the spectral index business, it doesn't change between its value at the end of inflation, where alpha tractors is a good description of the model, and the moment of after the enhancement of the perturbations. This is a particularly nice result that we found. And on the tensor to scalar ratio, well, if we have an enhancement on the scalar sector, then it immediately translates into a suppression on the tensor to scalar ratio, because the tensor modes are not affected by all of this story. And so let me mention very briefly the requirements for this post-inflationary enhancement. in contrast to the one I talked at the beginning, where already during inflation we have this sourcing of perturbations. Basically, we require two things, namely that at the end of inflation, the amplitude of the isocurvature perturbation and the amplitude of the curvature perturbation are more or less of the same order. This is because you can think it as follows. If by the end of inflation, we don't have any isocurvature, then no matter what happens after the end of inflation, we will never find an enhancement. And this is due to the fact that if we consider a mock plot of the power spectra for a massive mode, if the mode is very massive, let's say the green curve, it has a huge suppression. And in turn, if it's massless, like the curvature one, it stays frozen. So we demand that the isocurvature mode is either massless or very light. So it is either on the blue regime or very close to it, which is indeed what happens in our case, because I told you that the mass of the isocurvature mode goes as 1 over n squared. So it is almost massless or quasi-massless. So this achieves the goal of having enough amplitude in the isocurvature mode at the end of inflation in order for it to source the curvature mode after the end of inflation. And the second condition is basically to have a substantial turn rate after the end of inflation. And we can easily understand the condition to realize this as avoiding initializing the field at its minima. Here I plotted a very easy example. If we start the field at its minima, let's say the blue trajectory, even after during the end of inflation, the field will never turn because it's already aligned with the minimum. So we never look for the minimum. So no turning, no sourcing, no nothing. On the opposite regime, in the red trajectory, during inflation, we remain fixed as in the model I presented you. And after the end of inflation, the fields start to look for the minima, and then it's the moment where the background starts turning. Just to summarize, we demand that the isocurvature mode is either massless or very light, and that we are not aligned with the minima when initializing the fields. And with that, we can expect that there is a post-inflationary enhancement of this curvature mode. And just to show you another example, in order to not to arrive at the conclusion that this is special for the modular case, or that this effect of the post-inflationary enhancement depends on the modular symmetry. Here in the paper, we also cooked up this Tanch model. This was completely by hand. This was just to showcase that, again, our results do not rely on the modular invariance. Here, as you can see, all in this model, also the theta direction is heavily suppressed. It is not double exponentially suppressed, but it's heavily suppressed. And again, we have the alpha tractor expansion in the phi direction. So once again, I am here showing you the background motion during inflation in solid lines and after the end of inflation in dashed lines. And once more, we find that during inflation, basically the background doesn't feel the theta direction, it stays fixed, and we only move along phi. But after the end of inflation, we start heavily turning, looking for the minima of the fields. And thus, we expect similar results from the previous model, namely that during inflation, the turn rate is heavily suppressed by this large factor here, and thus, during inflation, the left-hand side, we don't see any sourcing of perturbations. The curvature perturbation in blue evolves independently of the isocurvature perturbation in yellow. They don't feel each other. However, suddenly after the end of inflation, they suddenly notice each other via the heavy turn rate. And again, we find this net enhancement of the curvature perturbation due to the isocurvature one. And here again, I am showing you also one of the requirements that I told you earlier, namely that the isocurvature mode is again very light. In this case, it's again light because it goes as 1 over n squared. And so in order to start concluding, I have talked a lot about post-inflationary effects. However, we know that after the end of inflation, the universe is left in this cold and void state, namely that whatever matter you put in an inflating universe, it will dilute very quickly. And this does not match the Big Bang conditions, namely doesn't transition naturally to a radiation-dominated epoch. So we have to reheat the universe via the mechanism that you like more. In this analysis, we didn't take into account any reheating information. We only neglect reheating 3 effolds after the end of inflation, and a way to quantify this effect on the reheating period is as follows. We know that our results rely on the background motion, namely because the background motion gives rise to the turn rate. And we know that the background dynamics are governed by, for example, the equations of motion of the two fields when gamma is equal to 0. And thus, we can model some perturbative reheating process by introducing this gamma factor here to the equations of motion, which then encodes a dissipative term that is shedding some energy or some energy from the fields to some other degrees of freedom that will eventually reheat the universe. And then we pose the question, what is the maximum value that gamma can have in order for us to safely neglect it 3 effolds after the end of inflation? We did this numerically, and we find that gamma has a specific value that can be translated into a reheating temperature. So we found that in order for us to safely neglect any reheating information up to 3 effolds after the end of inflation, this reheating process can happen at most at 10 to the 13 GeVs, which is a very broad window still, because we can go from this number up to, for example, the BBN temperature, as reheating is a very broad window. But at least in this way, we are setting some constraints on the applicability of our calculations. And so my last slide is basically to say that whenever one works in multi-field models of inflation, we should not close our eyes to what happens after the end of inflation, because it may very well be that even after the end of inflation, we still have an active sourcing of perturbations that needs to be taken into account in order to properly set the parameters of the model. And this can have it's a way to correctly assess the observables. And again, even though we worked in this modular model, we don't have a reason to believe that this is unique to our model. So whenever the two conditions that I told you about, namely a light isocurvature mode and a heavy turning after the end of inflation, are present, we expect to have the same post-inflationary enhancement as the one I showed you now. And with that, I finish. And if there are any questions,